All right, good morning. Let's get started. So my name is Prateek, and I'm going to talk a little bit about Linux. Just to show of hands, how many people have heard of Linux? Heard of Linux? Okay. Used it anywhere? All right, that's good. So a brief overview. I'm going to start with a bit of operating systems history and try to see how we got to now. Look at the kernel architecture of Linux. It's a big system, so try to help you navigate the source code, although you might not need that for the course. And we'll see some of the implementation highlights and some of the practical considerations that arise when you are implementing a big production level operating system kernel. Oh, and if there are any questions at any point, just holler. Okay, so we'll start at the beginning of time, literally, with Unix. So January 1st, 1970 is the sort of start of Unix time, right? So Unix was this great operating system created at AT&T Bell Labs, which introduced several radical concepts and really small, implemented in a high-level language, C, and gave us a lot of useful abstractions like files and processes and shell, and the fact that text files can be a fundamental building block of a lot of complex tool chains. So things were great for a few years until we reached around 1990, when unfortunately patents and some copyright issues between AT&T and Berkeley left Unix in some kind of a state of limbo. You really couldn't use it freely, which you could earlier, right? And then there was a whole new class of hardware devices, personal computers, which were becoming really popular, and you couldn't really run Unix on your personal computer, right? And that was bad. A lot of people actually wanted to run a good operating system Unix on their PCs, right? And it couldn't be done, right? So what's the solution? Right? So around this time, or slightly earlier, there was another standardization effort, which was called POSIX. Right? So in the 80s, there were a lot of Unix variants going around. So AT&T had their own version of Unix. Berkeley had their own version of Unix called BSD, the Berkeley Software Distribution. You had a lot of companies, Sun, IBM. For a brief while, even Microsoft had their own version of Unix. So everybody has their own version of Unix. The source code initially was out in the open. They just modified it, and they created their own slightly incompatible version of Unix, right? And this was a problem to be solved, and there was a POSIX standard developed, which basically said that, look, this is Unix, right? What that was a set of system calls and the behavior of those system calls. So if you implement any system, maybe from scratch, and if you stuck to the standard, if you stuck to the POSIX standard, you had Unix, right? So Richard Stallman, he created this GNU project, which stands for GNU is not Unix, a nice recursive acronym, which was basically a freely available software tools which could mimic Unix functionality, right? And so what tools am I talking about? You need a shell interpreter, right? So you have the shell, you need to compile and link and run programs. So you have all these things. You have the GCC, the GNU compiler, which comes here. And then you have other utilities which are really the core utilities. You have commands to copy, move, awk, sed, less, grep, all these things. And so the Free Software Foundation created these set of utilities which were sort of free for anybody to use, right? So it's free as in freedom, not free as in free beer. That is, you could take the source and you could do whatever you want as long as you redistribute the source when you actually sell or redistribute your binaries as well. All right, so GNU was great. You could finally run all your favorite Unix utilities. They were bug-free, high performance, a lot of features. Everything was great. But there was still this nagging problem that you actually couldn't run these things on your PC, right? The PCs were cheap, they were very, becoming cheaper and faster, but you still couldn't run it. So what are the solution? So along came Linus Torvalds, who in '92 created the kernel. The kernel is a piece of the operating system which actually runs on the hardware, right, and sort of implements all the system calls, which all the user level programs use. So now you have this sort of Unix compatible kernel called Linux, right, which could run on the 286, which was a PC which Linus had. So that was the first supported device. And B, it was sort of POSIX compatible, so you could run your existing GNU programs on top of Linux, right? And along came all these distributions, which basically took the Linux kernel and a big subset of the GNU programs, bundled it together on floppy disks, right? And they became Linux distributions. So you had Red Hat and Slackware, and Debian, and now Ubuntu. So roughly it looks like this. You have, your hardware platform on top of which runs the kernel, right? Which sort of has the system call interface, which is used by all the user level programs. And combined, this so-called thing is called GNU/Linux, because a lot of these user level applications and especially the C library is actually created by GNU. All right, any questions? Okay. So the good thing, so it started off as a kernel which ran only on the 286, but now Linux runs on everything, right? It runs on most of the servers, it runs on most phones, it runs on almost all embedded devices, supercomputers, and occasionally some desktops. All right, so before going on to how Linux works and basically why it can run on so many devices, let's look at the high-level component diagram of the kernel itself. And I hope by now the difference between the kernel and the entire operating system sort of is clear, right? I mean, we are only going to focus on the kernel, which is the part which sits right above the hardware and implements the system calls. All right, so obviously to talk to the hardware, right, you need to support that hardware, and you need to have the so-called device drivers, as well as the architecture-specific code which actually runs specific to every architecture. So, for example, the Intel 386 or the AMD 64 architecture, right? These are examples of architectures. The ARM, which runs on most phones, is another example of an architecture. So you have this sort of very low-level code which actually talks to the hardware at the bottommost layer. And then once you have that ready, you can do a whole host of things like process management, memory management. You can implement your network stack. You can have file systems. And finally, you have the system call interface, which user programs basically, use to basically use functionality within the kernel. Okay, so before going forward, let's list some system calls. Who can give me some example of any system call? Kill, all right. That's a good start. What else? Yep. Fork, all right. What generally goes with fork? Open, all right. This is useful. We have open. Sorry? What is that? Wait, all right. Right? Fork. Exec. Right, that's a good list. These are indeed the main system calls, and we won't have time to go into all of these today, but let's see what we can do. All right, so the kernel is maybe now more than 17 million lines of code. So it's a pretty large program. Most of it is written in C. You have very small amount of architecture-dependent code, which is written in the assembly language of that architecture. So the x86 kernel will have, will have the x86 assembly language instructions, right, for really low-level stuff. And the unfortunate part is that the documentation is not quite up to scratch because things change so quickly all the time. So by the time somebody writes something about one part of the kernel, it's already changed 3 months from now when the next version comes. But still, the high level design and the high level architecture more or less remains the same, and those are the parts which I'll be going over today. Okay, so I mentioned earlier that the kernel is 17 million lines of code, and we had seen earlier that Linux runs on everything, right? Like almost any general purpose computing device, and Linux is going to run on it, right? It runs on the Sony PlayStation, it runs on nuclear submarines, it runs on these wireless routers, you name it. So how is it possible for this sort of one big program, right, to support everything? Right? So if you look at, for example, your wireless routers, right, they're embedded devices. They don't have a lot of memory. They don't have a lot of storage. They don't have a lot of processing power. Right? They're limited by their actual electrical power consumption. So the kernel needs to be, small and lightweight, and it needs to have a minimal memory footprint. Whereas if you look at a supercomputer, that doesn't have any of these restrictions. But then you have other features which a supercomputer needs, right? You need to be able to support those vast number of CPUs, right? A few thousand CPUs, right? You need to be able to address a few terabytes of main memory. So how is it that you have this one program, this one kernel which can run on really, really underpowered devices, as well as really powerful and really large computing platforms? Right? So the way around it is what are called kernel modules. So Linux is a monolithic architecture, right, as compared to a microkernel architecture. Are people familiar with that term? Monolithic? All right. What that means is that basically it's like one big program. So generally, if you are writing one program, right, let's say you're writing some C program or a Java program, that's one program. It runs in one address space, right? You can basically call any function which is visible to you. So if it's not protected or private in Java, you can call that function, right? No problem, right? That function is in that package. You can call it. No issues. Similarly, if you want to share data, if there's some linked list which two components or two classes want to add to, they can do that, right? That's not a problem. So Linux is a monolithic kernel, which means that it's actually one big program, right? The kernel is one big program. It's like one giant program, right? Which always works perfectly. Okay, so if you have this one big program, how are we going to make sure that it runs on every possible device? How does that happen, right? You can't have this one big kernel which runs on a small wristwatch, for instance. That would be overkill. So the way around it is what are called kernel modules, which are basically pre-compiled executable objects which can be dynamically loaded and unloaded at runtime. Okay. And we'll see examples of modules and how they work and what kind of modules exist. But in general, you can think of it as you have one small, so the kernel is like one small program, right? But you have these other modules which can be added to this one small program, and then you can implement any functionality that you want. But it's still in one address space, so the modules can still access any code and any data which is present in other modules or in other parts of or in other parts of the kernel. And that's one of the key features of the monolithic system, is that anything can call anybody else. You don't need message passing. You don't have address protection within components. All right. So any questions about kernel modules? Okay, so let's see an example, right? Let's go here. So, oops. All right, so this is my Linux box, and let's see what modules I have loaded on the system. So, come on, for doing ls mod. Maybe we can see that. All right, so these are all the mods. So the ones on the left, they are module names. Right. So I have, for example, a SCSI disk, so I have a SCSI transport module, right? Similarly, Let's go up and see something interesting. I have IP tables for network packet filtering, which I need. I am running the FAT file system, so I need that as well. NTFS file system, so I have a separate kernel module for that. XFS, so these are all file systems, etc. Right, so these are the modules which are sort of loaded right now in my system. Right? And you can dynamically load and unload a module. Right? So let's see, let's try to remove one of the modules and see what happens. Right? If you have an attached hardware device, so let's say if I have this projector connected to my laptop, right, and there's a module which is supporting this, right, and if I try to remove the module, it might complain because look, I need to use the projector. So let's try to remove a module which may not be needed. So let's try to remove this Bluetooth device. I don't need the Bluetooth module. So it's error. It's in use. So there's some part of the kernel which is actually using that module, so you can't remove that. Let's try this one. Yep. So now I've got rid of the USB Bluetooth module, and now I can get rid of Bluetooth altogether. There you go. Okay. So using this, so as soon as a module is not required, the kernel will dynamically unload it, and so the size of the kernel which is running in memory, it remains fairly small. Okay, so let's see our first example of the Linux source tree. Let's start with the modules. Right, so this is the sort of the entry point of module loading and unloading, right, for the x86. So as you can see, it's all C code. That's one of the first observations that we can make. And then you have code for basically, so the way it works is that you have ELF relocatable objects, which are the modules, and which are actually then linked onto the running kernel by this code. Okay, so in general, let's start at the high level, right? So this is the source tree. This is how it looks like. You have the architecture-specific code here. You have the block devices, code for the block devices here. A lot of cryptography code, drivers which support all the hardware out there. Code for dealing with some of the firmware. FS is file systems. This includes all the headers which the kernel itself uses internally. So for instance, if you want to do things like, if I want to print a string, I don't have printf available in the kernel, right? Printf is implemented by the C standard library, which doesn't yet exist, right? Because the kernel runs directly on the hardware, so it needs to have these kind of standard library functions of its own, right, for its own use. You have things for inter-process communication, memory management, networking, things for dealing with sound, virtualization, etc. Right, so this is where all the 17 million lines go. Questions? Yeah.
I was just wondering what you meant to start running.
Okay, so the way you do that is called mod probe, and this basically will check if the module exists and its dependencies. So for example, we saw here that the HID module depended on the USB HID module, right? So there was a dependency, and mod probe is smart enough to basically resolve this dependency. So if you have a module which depends on other modules, which depend on other modules, if you try to load this top level module, it will basically try to load all the other modules that it depends on. All right. So here I basically reloaded the HID module by using mod probe. So mod probe HID, and I have loaded that. Let's see if it's loaded. Right, so I have the HID module over here. All right, great. All right, so those were kernel modules, and that's one of the great features of Linux, that you can have a kernel which supports everything and every device and every file system and every network protocol and every security encryption service, but yet you can sort of pick and choose. You can sort of pick and choose what you want. So let's see how are you going to do that, right? So before that, let's see, how do you compile a kernel, right? How do you basically, so let's say I have a new device, I've got a new desktop, and I want a kernel for that, right? So any guesses? So let's say I have this brand new laptop, right, which might have some new hardware devices which I don't know about, and I'll load up some distribution, let's say Ubuntu, right? So how do I figure out, what modules to load, and so because the modules which I need to load are dependent on the hardware which I have, right? So I may have this really fancy NVIDIA graphics card, but if I don't have the driver for that, it's not going to work, right? So let's see how that sort of happens. So each hardware class, each hardware device will have an identifier string, right? So I'm this NVIDIA GTX graphics card, and then the kernel will basically probe all the hardware devices to get these strings, and based on that you have a table which says if you have this string, you load this module, right? And that's it. So if you plug in a device, it will query the string and load the module. So in general, since this is basically since the kernel is one big giant C program, right? How do you compile it? How do you compile a normal C program? GCC. All right. What command do you need to use? So this is a big program, right? This is like thousands of files and millions of lines of code. Make, exactly, right? So the way you do it is you type make. So this is the Linux source tree on my local machine, right? This has all the same directories. This is kernel version 3.2. And if I type make, I'll be looking at 2 hours of scrolling messages because it takes 2 hours to compile, right? On a fast machine. All right, so that's make. Now, let's say, I need a specific feature of the kernel, right? I need to know that this feature exists in my kernel, right? Or I need to configure a brand new kernel of my own, right? I made some change, and I need to select this feature, and remove certain features. So what you can do is you can configure the abilities and the features which are present in your kernel. And the way you do that is basically make menu config. Right, so this gives me this nice n-curses based sort of graphical interface to select what are the features which are going to be included and excluded from this new kernel which I'm compiling. Right, so let's look at general setup. So let's say I don't want System 5 IPC, right? That's things like shared memory and message queues. I can actually deselect this, right? So my new kernel will not have support for System 5 IPC at all, right? Let's select it back. Right, so these are all, so it has tens of thousands of such options which you can fine tune, right, to get exactly the kernel that you want, right? But mostly you will not have to use this because the Linux distribution which you generally use, like Ubuntu or Debian or whatever, they have already pre-selected these options for you, right, which are sort of optimized for desktop use and for most users. But this is fairly a cool way to basically optimize your system, right? You can remove things which you don't need. If you're running a laptop with no Wi-Fi, why do you even need the Wi-Fi modules, right? So things like that. Any questions? Yep.
So would we just configure more of the kernel?
Right. So you first have to make menu config, which selects all the configuration options. So it's basically it's like running configure. You basically configure whatever features you want, and then you call make, and make basically build all those things. Okay. Let's exit from here. Okay, so that was kernel modules. Now let's look at Linux system calls. Right, so we have already a nice list of system calls here, and we're going to see how basically programs can call system calls and how they are implemented in the kernel itself. All right, so the syscall gate is here, right? Which is basically, as you can see, when you call some system call, this is the point of the kernel where it comes to, and you might be wondering, like 33 lines, that's it? That's a code for like implementing all system calls, and it's a fairly clever design. So what happens is that you basically have this one table, right? You have a system call table, which contains function pointers. Right? So if you have 100 system calls, it's going to contain 100 plus 1 function pointers, and each function pointer points to the function which actually implements the system call. So for instance, come on, this is just silly. Right? If you see what are the system calls available in my system, I have this kind of a table. I have the system call number, which is 0. I have common, which says that this is for 64-bit or 32-bit systems, and I have the system call name, read, right? And this represents the function pointer, so it's going to call sysread, right? So we managed to list about 6 system calls here. So on this system, I have support for a whooping number of almost 554 system calls. Right, so that's how complex the current kernel is, right? We just kept adding more and more system calls, and of course, you can add your own system call, right? If you want to add your own system call, you just add an entry into this table, and implement this function pointer, basically this function which this function pointer points to, and you're done. You have your brand new system call. So that's pretty cool. So we have seen the table, and we have seen the mechanism in which the system call is actually called. Right, okay. So let's look at a practical example, right? Let's look at what are the features that Linux gives us. So let's say I'm debugging a program, right? I've written a program in C, and I want to find out, what are the system calls that it's calling, right? So how do I do that, right? I have this program, maybe it's running already, or maybe I'm launching it, and I want to know, what system calls am I calling? So it can be useful to get things like performance or even correctness, right? So if I'm issuing too many disk, read or open operations or forwards and execs, I know that may be a source of bottleneck. And the command to do that is strace. So I have strace, right? It stands for system call trace, and then I can give any executable, right? So let's say ls, and let's see what possible system calls might be executed when I type ls. And here I go. So the good thing about strace is that it gives me the system call name as well as the commands as well as the parameters which it has passed. Right. So the first thing it does predictably is calls execve, right? So as soon as you fork, you call exec with this. So this is the location of a binary. Then you access a few files, mmap, open, fstat, access, etc. And as you can see, these are all basically the directory entries, right? Okay, so that was strace, a fairly cool feature to help in debugging. One of my favorite tools. All right, now let's look at some low-level code and see what exactly happens when you call a system call. So as you can see, this is not a C file. This is a .s file. So it's assembly, and this is the entry point for the kernel from user space. The description says it's fairly for handling low-level faults and for handling system calls. Inline assembly here, and that's it. This is basically the one of the key parts of the kernel, which actually makes sure that you copy all the registers and you call the right function pointers, etc. Questions? Yes.
And also use S3 to trace a C program or Java program or
So if you have your own C program, right, and if you don't know what system calls I'm making, you can do that. Absolutely. You just pass the name of the program to strace. Yes.
the name of the program.
Right. So for example, if you write a program, whatever a.out, right? That's your program name. Just say strace a.out, right? So the first parameter is the name of the executable. You can have any executable that you want. I can have, let's say. So we did this mod probe command earlier, right? This ls mod command, which says what are the modules loaded. I want to know what system calls that makes. Let's see, right? So there we are. So in general, like any executable, you can do that. Yeah. So thing is, if you pass it a Java program, the problem is that the Java program runs via the Java virtual machine. Right? So the JVM is going to actually be making all those system calls on behalf of your program. So it might get a bit messy to see what exactly is happening in your Java program if you look at its strace output. Good question. Yes?
Those equal, like right equal for the that were returned.
Yes. That is the return code. Yes. Yeah. Good point. Yeah. So you call this system call write, and you got the return value 33, which probably is the length of the string, I guess. Yeah. All right, super. All right. All right, now let's look at some of the things which you might have covered in class. Feel free to stop me anytime. And basically see how these things are actually implemented in Linux. So I assume that you have studied processor scheduling, memory management. What about file systems and I/O? All right. No, yes. Yes, all right. And then we look at some kind of, if you have time, we look at some synchronization operations, right? You have probably studied about spin locks and mutexes and semaphores and all that. And the kernel actually implements all these things itself and provides these things to the user programs. And you might see how these things are actually implemented by using hardware instructions. So CPU scheduling. What are some examples of CPU schedulers? Process scheduling algorithms. Yes. Round robin. Okay. MLFQ. What does that stand for?
Multi-level feedback queue.
All right, multi-level feedback queue. Okay. And how complex do you think these are? Let's say round robin, right? How hard can it be? You pick up one process, put it at the back of the queue. When it's done. Okay, so let's look at the Linux scheduler. And all right, who can guess the size of this file? Lines of code. 10,000. That's a good guess, 10,000. Fairly close, right? So it's close to 8,000. This is just one file, and the CPU scheduler is implemented in many files, right? So it's hairy, and it's one of the very complex piece of code because it has to handle so many edge cases, and again, it has to work on low power devices, it has to work on supercomputers and make sure that it's low latency, high throughput in all cases, etc. Okay, so in Linux, so this basically implements something called what is that? CFS, which is a completely fair scheduler, which basically tries to make it maintains a red flag tree of all process times, and it allocates processes some time pointer to use, right? And the process which sort of has the most time pointer left is allocated, is basically scheduled on CPU first, and so on. It's a fairly simple, the algorithm, CFS algorithm is fairly simple. It's not involved at all, but its implementation is really challenging. Okay, so we have looked at CPU scheduling. Questions? Okay. Now let's look at let's look at this thing. So this file basically contains the high-level file read, write, and open operations. In Linux, basically the file system operations and memory management are kind of intertwined. So this is actually in the subdirectory, the memory management subdirectory, and that actually contains all the code for file open and read and write and so on. So you might want to be aware of that. So here it is, like, generic perform write. You're given a file, you're given a position, and you're given the IO vector. Right? So this is where a lot of these system calls are actually implemented. Okay. Let's look at context switching. This is the one function which actually does the context switching. Switch to, you have a previous process. Linux refers these two as tasks. So you have the previous task and the next task, which you want to context switch to. And it's actually fairly well written. This function is really well written, and you can really actually make sense. You basically save all these segments. You save your ES and GS, and obviously your DS, and so on. You save these segments because you want to save the state of the earlier process. So you save this. Then you basically, this is the architecture dependent code, right? So this is the x86 dependent code is going to be called, which issues these special instructions to copy the rest of the things. Then you switch your FS and GS segments, and that's it. You're done. So it's pretty sweet. So this part of the code is really good. All right, let's look at fork. Right? Let's look at how fork is implemented. And we come to do fork. You have the flags, which I'll explain later. And you have the parent TID pointer and the child TID pointer, and the copy process. I'm going to basically now copy the address space and other things of the process into the child, right? And that's it. And it must be said that the Linux fork implementation is extremely optimized. Right? There was this whole thing earlier about operating systems that process forks are expensive and you should not have a lot of forks. That's why you have threads and so on. But Linux fork, in fact, even if you do a thread clone, it goes through the same path, right? The same function is called even if you do a process fork or a thread clone. So they have really optimized this function right down to the last instruction, so to speak. Okay, so you might have studied about the process control block. Have you? Process control block, alright. So what are the fields in the PCB? What should this contain? Program counter, okay. So you have this register. Yep. Stack, okay. Sorry? The heap. Okay, so let's actually copy this. We have the address space of the process. What else? PCB. Yep. Sorry? The code to be executed. Okay, so you have which comes with this. So this is basically equal to the code section plus all your data plus stack. Yep.
Page table pointer.
Page table pointer. So what comes with this plus page table. So in fact, not just the page table pointer, but all the page tables of that process itself. Yeah. Yes.
The base registers.
Base registers. Okay, so you have let's call these the CPU registers. What about the simple things like the PID and all those accounting process accounting information, right? So you have the PID, the owner, who's the owner. I have this sort of time accounting, etc. Now let's see if these things are indeed present or not in the Linux task structure, right? Let's go here. Here we are. This is the task struct. One thing which we forgot was state. Is it running, interruptible, stopped, things like that. You have the stack, you have the flags, and it's a big structure. It's a really, really big structure. Finally ends somewhere. Yep. Finally ends here. So it contains a lot more things than what you might be aware of. But a lot of things are like about tracking and security and accounting and tracing and things like that. So this is the state for the virtual memory system, and you have the backing device, the I/O context. What are the files which it has open, and file table and so on. So there's a lot of stuff in there. All right, questions about fork implementation or processes? Yes.
I was wondering how fork returns two different things. Because it returns like the ID to the child.
Right.
And one to the parent.
Right. So again, that's so there are two things for that. So as far as the kernel is aware of it, it's just a fork system call, right? And you have two things, right? So because you have created these two processes, it can write two values into the address where the process expects a return value, right? And since in the kernel you have these two processes, right? One is the parent and one is the child, the newly created child. You can write these two values into these two processes. Yes. So remember that the kernel is basically supreme. It can write any value into any address of any process. Right? Yes. Sorry?
Who wrote the code for that process control that? Was it like a single person?
Oh, that's a great question. So who wrote all this? Who wrote all these 70 million lines? So initially it was written all by Linux. When it first started for the first few months, and then it just picked up. And so this basically, so what happens is that every subsystem, basically, so if, for example, every architecture and every feature, so the file system, the networking, and all these things are going to be maintained by separate maintainers who sort of have control over what goes in and what goes out. And then you have this few 10,000 sort of volunteer army, so to speak, who are not who are not exactly volunteers, who basically write some of these things. So what happens is that it starts off really simple. So the task structure, the process control block when it first started, basically just had these things, right? But then people kept adding more and more features, and then implement more things. You need to add more fields and so on. So yeah, but that's a great question. So it's a big mess. So this file, let's see who's the maintainer, and I don't think it's going to be there, right? But yeah, this is a header file. Header files generally don't have maintainers, but if you look at, I think it's Ingo Molnar. He's the x86 maintainer, so it's probably him. Okay, so we have covered some parts of the kernel. That this is the sort of interactive detailing kernel map, which sort of shows how the various subsystems interact with each other. Right? It's a fairly easy way to understand what's going on. So you have things called the system, processing, memory storage, networking. Further here, you have different layers. You have low-level device control, then you have logical devices, then you have further higher-level logical devices, then you have the virtual device abstraction, and then finally, here's a user-level control. So here's a system called etc. Top level. And this is a fairly nice map which you can play around with. You can sort of zoom in here and show each file. You can go here. So with this map, you can sort of see if you want to find out wherein some piece of code, so which file implements this functionality. You can sort of use this to navigate around, things like that. So let's see. We wanted to see where the fork might be implemented. That is in the processing subsystem. And so these are all system calls, right? These point to system calls, and sysfork is the top level implementation of fork, and finally do fork, which is the actual implementation of fork, right, which we saw right now, right? So sysfork is, let's go to sysfork, sysclone, sysfork, and let's define somewhere here. Right, so this is basically the function pointer, which is there in the syscall table. As you can see, just okay. All right, so this table is interactive map is pretty helpful. We have already seen how to compile your own kernel. Just download the source, make config. Make config first to select what you want. Make modules and header, and finally install it. Questions? Okay. So sometimes if you have compiled your own kernel, or you just want to know, what the heck is my kernel doing? What's my system up to? Why is it behaving this way? The first thing to check is the logs. The kernel has print k, which is the equivalent of printf. So let's look at the logs, right? Let's look at what my kernel is telling me. And the command for doing that is dmessage. So here you can see this basically starts at time 0. So all the boot logs are here, and you can see at the bottom, I don't know if you can see this, but we removed the USB HID device module earlier, and that has shown up in the log here. Is that DDR string interface driver USB hid. So one way to look at is the logs. The other way which we have seen is strace and things like that. Linux also has this really useful sort of file system called procfs or sysfs, which is basically you can control your kernel by just reading and writing from files, right, while it's running. So what I mean by that is if I go to /proc, I have all these files and all these directories. Each directory actually represents a process. So this is basically, so these are all PIDs of processes running in my system. And these files tell me very useful information which I want to know. So for instance, I want to know my CPU info, right? Since this is Unix, all I need to do is dump this file here. And it tells me information about the CPU which I'm running on. Right? So remember, this is like low-level hardware information which is available only to the kernel, right? Because it hides all these things from users. But users can sort of interact with the kernel through the proc file system. And you can also set and sort of reset some kernel parameters. So if you want to tune some parameter at runtime, instead of compiling the whole thing, you can do this by just writing a value to the proc file system. So for instance, if I want to clear out all the caches in my system, I would want to do that for experiments, let's say. So if I'm running a program once, and if I'm running it again, the performance might be affected because I have all these caches in my system, right? So if things are already cached, and in the second run, I will have much better performance than I had in the first one. But that's a result of the caching effect. So if I want to clear out the cache, where is that gone? It's not here. Anyway, so what you can do is basically you can write values to these files. So let's say I am to run, if I want to run this kernel, if I want to stop this from running, I can just write the value 0 to this file, right? And this is a way to control functionality of the kernel. So you can sort of read the status as well as set some parameters for it to run. Okay, so that's pretty useful. And so recently the kernel has this really sophisticated kernel tracing techniques. What that allows you to do is it allows you to trace in real time like every function call which is made inside the kernel. Right? So every function call, every function exit, you can trace that in real time using sort of tools like ftrace and perl. And lastly, if you really want an interactive debugger, the question arises: how do you debug your kernel? Right? So you need to run something under the kernel to debug it, and there are two ways to do it. One is you have a separate machine which you connect to your machine via a serial interface, and then you control that machine remotely. The other is you run it inside a virtual machine, and with this you can easily attach a debugger to your kernel and basically do normal things like set breakpoints and step back and so on. Okay, so lastly, let's look at some of the things which why is Linux so popular and why are people using it. Well, I think it's a good implementation of some very good Unix ideas. And people have always wanted some Unix-like operating system for a long time. It's got this huge open source community composing of tens of thousands of developers, which are highly skilled and know the kernel inside out, who can submit bug fixes and new feature patches and so on. And it's got like, really good scalability. It can scale to a large number of processors with very high efficiency. It's got this very nice GPL version 2 license, so that anybody who makes a modification to Linux and redistributes that modification must also distribute their own source code modification. So this allows basically, this prevents lock-in, right? So there's no commercial entity which can take Linux, make changes and then sell it without distributing the source also. So like any changes which you make to Linux, which you want to distribute to others, you must also distribute the source code of these changes. That's one of the main reasons this viral clause has made Linux into what it is today. And there are many other Unix variants which share a lot of these qualities. So FreeBSD is the latest versions of the long line of BSDs. We have Solaris and its derivatives like Illumos, etc., which are also very good implementations, also very high performance, also have good licensing, and they also share a lot of these good features which Linux has. Questions? Yes?
Isn't like Apple operating system based off Linux?
Okay, that's a good question. So if you go back, that's a really good question. So let's look at this, right? So what happened is that there was a standard created called POSIX, which was a Unix standard, right? What that meant is that any system which implements the standard is called Unix, right? Can be called sort of Unix compatible, right? So Mac OS 10 is actually POSIX compatible. What that means is that it supports all the system calls which Unix is supposed to support, and it implements those system calls in a way that is compatible with other Unix systems. Right? So if you have let's say a program and you run it, it runs on Linux. There's a very high. It's very easy to port it to Mac OS as well if you have the source code. Right? So there are a lot of variants of Unix. Mac OS is a Unix. You have Solaris, we have BSDs, we have a lot of types of BSDs, we have Linux, we have Minix, and so on. So they're all Unix because they all support the POSIX standard.
So they don't have to release their source code?
They don't have to release their source code because they have implemented it on their own. They have like created this POSIX layer, right, on their own. Not so it's independent of Linux, completely independent of Linux. So in fact, it's based on FreeBSD. Right, so Mac OS uses a lot of BSD code, and BSD code doesn't have the GPL license. BSD code says that you take the source code and do whatever you want with it. So what Apple did was they took the code, they made changes, and they don't give back the whole community. Excellent question. All right, so lastly, if you want to learn more of what's happening in Linux, I encourage you to look at the kernel mailing list, which is where all the patches get posted. A lot of flame wars happen between Linux and others. For general Unix design principles, Monisbach has a really good book. And so Linux was all started because Linux wanted something which was better than Minix, which would run on his system. And Minix is a microkernel-based Unix derivative, which is meant for educational purposes. So its source code is small and fits in a book, in that book. And that's a good source to see about operating system design and actual implementation of real operating systems. All right, that's it. Questions? Yes?
Is the source of the operating system usually the distribution itself, right? You can find it like online.
The Linux source?
I have a distribution of Linux. Did I find the source code on there?
Right. That's a good question. So which distribution do you have?
What?
Which distribution do you have? Ubuntu. Okay. So in general, you will not find the source on your hard disk, unfortunately. However, if you look at the packages, if you look at the source packages, so if you have the Linux kernel installed, if you look at the Linux-source package, then you have the source for any package in your system. So if you have a package Linux-source, right? So that's the kernel source. Or you can just go to kernel.org and download the latest kernel that will give you the source.
I know it was all on that website, so that looks pretty, that looked pretty good.
Yeah. The map?
Electrons.
Yes, yes. So that's a good browsable way because the source is big and confusing, and this is like browsable and click. All right, that's it. Thank you.